Welcome students. The topic of our today's lecture is the moment of a force, and in this lecture we will talk on these subtopics. First of all, I will give an introduction to the moment of a force, and then we will talk about its unit and mathematical form, and then we will talk about the unbalanced condition, that when a body will be in balanced condition. And based on these concepts we will talk about the design of cranes, that how cranes are designed to safely carry the loads, and then based on the unbalanced condition we will do a numerical problem. So let's dive into the topic. Before going into the definition of the moment of a force, let's talk about the effects of a force. Effects of force. So force can have a translational effect. And what this means is force can move a body in its own direction. Translational effect. Suppose here a book is laying on a table, and if we apply a force to this block, the block will move in the direction of force. This is the translational effect of the force. And force also can have a rotational effect. That is, it can rotate a body when it is applied to a body. So the topic of our today's lecture is the rotational effect of force. Before this we have covered the translational effects. So let's take an example of the opening of a door that will illustrate clearly the rotational effect of force. So this is the top view of a door connected to a wall. This is the wall. When you see a wall from the top, you will see just a strip, and this is the hinge. The hinge is that part of the door about which the door will rotate. You can clearly see in the picture. And this is the door. This is the door. The same diagram has been repeated here. Now if I apply the force at the hinge, right in the hinge, the door will not rotate because this force is being applied on the pivot point. This force will tend to move this point like in this direction and its own direction. So here it will have the translational effect. It cannot rotate the body. So for a body to be rotated, only force is not the requirement. Force alone cannot rotate a body. Force alone cannot rotate a body. So what we need in combination with force, we need some distance from the hinge. The force should be applied at some distance from the hinge. Let's say the force is applied here in this direction. Now what will happen? The door will rotate in this direction, and the door sometime after the application of force will come here, like it will rotate about the pivot point. So we need the force to be at some distance from the pivot point, and we call this distance as d. We represent this distance from d, and that is called the moment arm. Moment arm. And what is moment arm? Moment arm is basically the perpendicular distance from the pivot point. Perpendicular distance from the pivot point to the point of application of the load, application of force. So the point of application of the force is this point here. The force is applied, and this is the pivot point. So the perpendicular distance between these two will be the moment arm, and we will discuss this later on, that what is the perpendicular distance between this force and this hinge point. Now what will happen if a force is applied in this direction? This force cannot produce rotation because its line of action is passing through the pivot point, and it is trying to pull the wall in this direction, and as the wall is hinged here, so it will not move in any direction, and it will remain stationary here unless we have a powerful man to pull this out of the hinges. So the second condition for a force to produce rotation is that its line of action should not pass through the hinge. When its line of action will pass through the pivot point, then we will not have any rotation. So first condition was the force should not apply at the pivot point, and the second is the line of action of the force should not pass through the pivot point. Now we are in a position to write a mathematical form for the torque. So torque is represented by a Greek letter. This is the Greek symbol, and we call it tau. This is called tau. So it is represented by tau, and the moment of a force is also called torque. So the formula for the torque is equals to the force times the perpendicular distance from the pivot point or the moment arm. So this equation is practical. If there is no force, there is no rotation, and if there is no d, there is no rotation at all. And d0 means either the force is directly applied at the hinge position or its line of action is passing through the pivot point. So now let's define the turning effect. So the turning effect of a force about a hinge or pivot is called the moment of a force. So this effect, this turning effect of a force about a pivot point is called the moment of a force, and this moment of a force is also called torque. So this is the equation for torque. Torque is equals to force times d, and d is the perpendicular distance from pivot to the point of application of force. Now let's talk about the unit of the moment of a force. So force is measured in Newton and this distance is measured in meter. So the unit of the moment of a force is Newton meter. Now let's talk about the d, or the perpendicular distance from the point of application of force to the pivot. Suppose the force is applied at 90 degree to the door. This angle is 90 degree. So you can see here, this is the pivot and this is the point of application of force. So straight away the width of the door will give you the perpendicular distance, or this is the perpendicular distance from here right to here. So this is your d. Now what if force is applied like in this direction, then you can clearly see that this angle is not 90 degree, and we will check the perpendicular distance between this pivot point and the point of application of force. So if I extend this, this is the direction of force, and the perpendicular distance here is this one. This is the perpendicular distance. So what is the value of this distance? You have to take this value, and this will be your d, or the moment arm. So you should be careful in calculating this d. Now let's talk again about the equation of the torque. Torque is, or the moment of a force is, force times displacement. So greater the force, greater will be the rotation or the turning effect of a force, and greater this d, greater will be the torque. You can see clearly from the equation. So this is the reason for the door handles. The door handles are made at a distance from the door. Suppose this is the door and these are the hinges. I am representing these hinges from the point. So the door handle is not placed here because d will be less. Not here, but it is placed somewhere on this region right here. So the reason for the handle to be far apart from the hinges is to get larger d, and we will rotate the door easily with a small force. Now let's talk about the unbalanced condition. So the moment of a force might rotate a body like in this direction, or this moment of a force might rotate the body in this direction. So if you look into a clock and see the clock needles, so the clock needles moves in this direction. So this direction is called clockwise moment. Clockwise moment. This moment is clockwise moment because this is in the direction of the clock needles, and this is against the direction in which the needles move. So this is anti-clockwise moment. Anti-clockwise moment. So for a body to be in balanced condition, the sum of clockwise moment must be equal to the sum of anti-clockwise moment. Sum of clockwise moment is equal to sum of anti-clockwise moment. Anti-clockwise moments. Sum of anti-clockwise moments. So the summation of clockwise moments must be equal to the summation of anti-clockwise moment. Then the body will be in balanced condition. Let's take the example of a seesaw to clarify this in balanced condition. Suppose someone is sitting here, and if he was sitting alone, it will have the person will have some weight, and if was sitting alone here, it will rotate the seesaw in this direction. So this is, if you can see, this is a clockwise moment. Now let's ignore this one, and suppose if someone else was sitting here, and it also will have some weight, it will rotate the seesaw in this direction in the absence of this body. So if you can see, this is the anti-clockwise moment. Now if we place these two simultaneously on the seesaw, then the net rotation will depend on the magnitude of the moment. This is the clockwise moment and this is the anti-clockwise moment. So the moment that has the greater value, the seesaw will rotate in its direction. Suppose if this was of a greater value, the seesaw as a whole will rotate in this direction in the presence of these two bodies. Now if this rotation, this anti-clockwise moment and this clockwise moment become equal, the seesaw will not rotate and this will be an balanced condition. So this was just the explanation of the unbalanced condition. Now let's take proper examples of the unbalanced condition. So consider this seesaw again, and two persons are sitting on this seesaw, one weighing 200 Newton and the other weighing 300 Newton, and both are at the same distance from the pivot point, that is 1.5 meter and 1.5 meter. So the anti-clockwise moment, and so let's calculate the anti-clockwise moment and the clockwise moment. So first of all, identify which one is causing the clockwise moment and which one is causing anti-clockwise moment. So this will rotate the seesaw in this direction, and if you can see, this is the clockwise moment. So we can write clockwise moment as force 300 times the perpendicular distance from the pivot point, which is 1.5 meter, and if you calculate this value, this is 450 Newton meter. Now this, if you look into this body, this will rotate the seesaw in this direction, and this is anti-clockwise direction. So the anti-clockwise moment is the force and multiply by its moment arm. So its moment arm, or the perpendicular distance d, is 1.5 meters, so we will get 300 Newton meter. And if you can see, the anti-clockwise moment is not equal to the clockwise moment, and the clockwise moment is greater in magnitude, so the seesaw will rotate in this direction, and later on you will see the seesaw to be like in this direction. It will have tilted in this direction. That means that the seesaw will have rotated in this direction. So the seesaw was not in balanced condition. Now let's again consider the seesaw. Now what we did is we have placed the second body at a distance of 1 meter from the pivot point. So this is the clockwise moment, and let's calculate the clockwise moment. It will be 300 times 1, which is 300 Newton meter. So this 200 Newton is causing an anti-clockwise moment, and this will be the force 200 times its perpendicular distance 1.5, and we get 300 Newton meter. And as you can see, the anti-clockwise moment is equal to the clockwise moment, so the seesaw will not rotate in any direction, and we say that the seesaw is now in balanced condition. So when the summation of the anti-clockwise moment is equal to the clockwise moment, then the body will be in the condition of imbalancing. So now let's take a general example of the seesaw. I will explain you what is meant by the sum. So suppose if one is causing a clockwise moment of 100 Newton meter, another person sitting here is causing a moment of 200 Newton meter clockwise, and one is causing a moment of a 300 Newton meter anti-clockwise moment. Then if we sum the anti-clockwise moment, it is just 300, and the clockwise moment, so 100 plus 200. So this was the meaning of the sum of clockwise moment and anti-clockwise moment, that we have to sum all the moments present, all the clockwise and all the anti-clockwise. Again we get 300 is equals to 300, and the seesaw in this case is also in balanced condition. Now let's discuss the crane stability, or the design of a crane, how cranes are designed to safely operate. So this is the diagrammatic view of a crane. This is the load arm of a crane, this is the controller's cabin, and this is the whole body of the crane. Now the load arm is made long. Why this is made long? This is made long because we want the crane to reach every part of the construction site, so that it can move the bodies or the other blocks backwards and forwards, and we want the crane also to lift the loads up to a higher altitude. So the load arm is made long for this purpose. Now when a load is applied here, suppose this crane is lifting a block, a heavy block. This heavy block causes the crane to rotate in this direction. So what will happen? If there is no safe mechanism, the crane will topple in this direction. It will rotate, it will collapse in this direction. Because the back arm is short, so they place here concrete blocks, heavy concrete blocks, and these blocks are called counterweights, counterbalance weights. And what is the function of these weights? You can clearly see that in this case the moment produced by the load is in clockwise direction, and these counterbalance weights produce an anti-clockwise moment, so they are actually balancing the torque produced by the load. So that's why these loads are called counterbalance weights. And now we have two moments applied to the crane. One is the one applied by the load and one is applied by the counterbalance weights. These counterbalance weights cater for the moment arm produced by this load arm and the load also. So in order to design a crane, this moment should be greater than the moment produced by both the load arm and the load. So this counter moment arm that is produced by the concrete block must be greater than the one produced by the load arm plus the weight. So if it is greater, then the crane will not collapse in this direction and it will operate safely. So you can observe that the concept of moment of a force is applied in the design of crane. So to have better operation of the crane, this counter moment should be greater than the moment of a load arm plus the weight. So now let's take a proper example on the unbalanced condition. The problem states that person F pushes the door with a force of 200 Newton at a distance of 20 centimeter from a hinge. So let's say this is the hinge and we assume that this is the pushing force. So the pushing force is 200 Newton and it is applied at a distance of 20 centimeter from the pivot point. Next, person B opens the door by pulling the door handle which is 80 centimeter from the hinge, and let's say this person is opening the door. So the distance of it from the pivot point, this total distance is 80 centimeter. What is the minimum pulling force that person B must use to open the door? So we are required to find this force, that how much force this person B must apply to open this door. Now if you see this 200 Newton force, or the person A is rotating the door in this direction, it is trying to rotate the door in this direction, and this is a clockwise moment, and this person B turns the door in anti-clockwise direction. This is the direction about, or this is the direction of the moment about the hinge, and it is anti-clockwise. So if this anti-clockwise moment becomes equal to the clockwise moment, then the door will be in balanced condition and it will not rotate in any direction. So let's first find the balanced condition. So sum of clockwise moments, sum of clockwise moment F is equal to the sum of anti-clockwise moment, then we will have no turning at all, sum of anti-clockwise moment. So person A is causing a clockwise moment, so it can be calculated as 200 Newton multiplied by its momentum, which is 20 centimeter, is equals to the summation of anti-clockwise moment. This person B is causing an anti-clockwise moment, so the force is unknown, let's call it F, and the distance of it, or the D, is known, which is 80 centimeter. So centimeter cancel out, and if we write for F, 80 will come here, and division it will become 200 times 20 divided by 80, 0 cancel, 2 cancels with 8, and here we left our with, and here we are left with 4, and if we divide 200 by 4 we get 50 Newton. So if this person B applies a force of 50 Newton to open the door, then the door will not open because the door will be in balanced condition. We requires that person B open the door, so the force must be greater, this F must be greater than 50 Newton. So for any value of a force greater than 50 Newton will cause the door to open. So this was all on the topic of moment arm, and in next lecture we will carry on the remaining topics. Thank you.